Hi everybody! Today we are talking about public key cryptosystems. We can also talk about asymmetric encryption, and it is important to remember that they have been invented by Diffie and Hellman in 1976. We have already discussed private key cryptosystems, where the key cannot be shared with other people, unless we want them to be able to read our messages. You will find the link to the video about private key cryptosystems in the description below. Here, things are a bit different. Alice and Bob are not sharing a common private key. Everyone who wants to receive messages needs to generate their own public key. So let's start with Alice. She wants to receive messages by anyone who wants to write to her. So she is generating her public key EA, where A clearly stands for Alice, and E stands for encryption. Then she shares her key with everyone. She doesn't have to hide it because it is public. So even if someone stole this key, she would feel safe. Then, if Bob wants to send a message to Alice, he will decrypt it with Alice's public key and send it back to her. Now, how can Alice recover the message? She will have to generate her own decryption key. Here, D stands for decryption. And this will remain private. Alice is generating KDA, and she will not share with anyone. That's a huge difference between public and private key cryptosystems. So the whole process goes more or less like this. Bob wants to send a message to Alice, so he first writes a message that we call text. Then he takes Alice's public encryption key and he sends to Alice the hidden message called ciphertext. Alice receives the ciphertext. She takes her own private decryption key that she applies to the ciphertext, and in this way she recovers the original message. If Eve, any third person, happened to read the ciphertext, she wouldn't understand anything, even if she had the opportunity to obtain the public key, because without the decryption key, she cannot retrieve the original text. However, this only works if Bob wants to send a message to Alice. But what if Alice wants to send a message to Bob? Well, in this case, first of all, it is important to say that Alice's keys are totally useless. In that case, the only way for Alice to send an encrypted message to Bob is to ask Bob to give her his own public key. That means that Bob himself should generate his public key, send it to Alice, so that she can send him an encrypted message. More in general, everyone who wants to receive a message has to generate their own public key. So Bob generates his pairs of keys, the encryption key, which is public, and he can share it with everybody, and the decryption key, which needs to remain private. Then the process goes exactly like before, but with Bob's keys. So again, Alice writes a message, she encrypts it with Bob's public encryption key, and she sends Bob the hidden message, the ciphertext. In order to recover the original message, Bob has to decrypt the ciphertext using his own decryption key, which he needs to hide from other people, including Alice. Again, like before, Eve cannot decrypt the ciphertext, not even if she knows Bob's public key. Now, let's try to summarize a bit. In a public key cryptosystem, every person involved in a conversation creates their own encryption key, which is public. From a mathematical point of view, we can represent it as a function which takes the plain text and transforms it into the ciphertext. But that's not sufficient. In a public key cryptosystem, every person should also generate a decryption key and keep it safe and private. From a mathematical point of view, it is the inverse function of the encryption function f. This is why we denote it by f-1. Okay, I can hear you. You may think that I'm cheating. Hey, we watched your video about private key cryptosystems, and that looks the same, a function to encrypt and its inverse to decrypt. Okay, I understand, but wait a second and you will understand the difference. The main difference is that in a public key cryptosystem, it is difficult to compute f-1 if you only know the function f. And by this, I mean that even the best computer struggles to compute the inverse function with the algorithms that we know nowadays. In a private key cryptosystem, it was actually easy. So this is the main difference. So how can this be possible? How can I generate both the decryption and the encryption keys, but other people can't compute the decryption key if they have the encryption key? The best way is to study some examples. The more, the better. So in this playlist, we will certainly study some famous algorithms you will find in some videos that I will add in this playlist. First of all, we have the famous RSA, a very number theoretic algorithm. Then we have El-Gamal, which makes use of deep algebraic knowledge. Moreover, we also have the elliptic curves cryptosystem and the hyperelliptic curves cryptosystems, which are exploiting some amazing properties of some incredibly powerful curves. Well, as you can see, cryptography is about to move very quickly into high-level mathematics. And that's not all. Some public key cryptosystems are nowadays used in some very famous applications. You certainly heard about them. For example, blockchains, and in particular, cryptocurrencies. For example, the most famous one, the Bitcoin, but not only. But that's it for today. Stay tuned because we need to discover many more interesting things. Please don't forget to like, comment, and subscribe. Thank you very much again. Bye.